Welcome to the second part of this video course. In this part you will learn how to perform some common day-to-day administration tasks. We'll start with a lesson about process management. Following that, you'll learn how to manage software using Yum and RPM. Next, we'll explore virtualization with KVM. After that, you'll learn about task management using cron and AT, which is followed by a lesson about setting up logging. In the final two lessons of this second part, you'll learn how to configure storage on your server. First, we will explore partitions, and next you'll learn how to set up LVM logical volumes. In lesson 10, you'll learn all you need to know about process management. We'll start by having a look at processes and shell jobs. That is followed by an explanation about Linux memory usage and performance load. Once you have a bit of an idea of what matters on a Linux system, we'll start analyzing the general system state using top. That section is followed by some explanation about process management, where you will learn how to change process priority and send signals to processes. At the end of the lesson, we'll do the end of chapter exercise, where you will apply some of the skills you've just acquired. On Linux, many services are started when your server boots up. These services launch all kinds of processes that are running in the background. You can use the ps command to get an overview of them. And you can see there are many of them. Let's see how many. By flushing it through the wc command, 456 processes in total. That's a lot. So everything that is happening on a Linux system is happening as a process, and you can manage it as such. But in some cases, users will launch commands from a shell environment. A command that is launched from a shell environment is becoming a job that relates to this shell, and from this shell you can get an overview of all the jobs. So let me just give an example by doing ddif equals dev 0 of equals dev null. I'm starting this job, which is basically a job that copies nothing to nowhere. And you can see that it is currently working on the shell, keeping my current shell busy. Now the thing about jobs is that whenever you start a job from the shell, it is keeping your shell busy. And as an administrator, that might be an annoyance, and therefore it is useful if you can move the job to the background. To do that, you would use Ctrl-Z. You can see my job is now stopped, and if I want to move it to the background, I can use the BG command. And now it's a background job in this shell. And I can start other jobs in the same shell. And if you use the jobs command, we can get an overview of all the jobs that are currently running. So jobs are always related to the current shell environment. And it's only this shell environment that jobs are related to. And if an administrator types a jobs command, he will see jobs only for his user account in this shell environment. Where processes is the total amount of tasks that are running on your system, no matter how they are started. And the difference between the two of them makes a big difference for managing the two of them. And that's why you need to be aware.
Every command that you start from the shell is considered a shell job. So if I type ls, that's a shell job. Many shell jobs just run and then stop immediately because they have done their work, which is the case for typical commands. But if you have commands that run a little bit longer, it can be interesting to do some management on the shell job in question. That means that you can put it in the background to complete its work so that you can continue to do something else. Let me show you, for instance, the command sleep 600, which is going to sleep for 10 minutes. If I press enter, then you can see that the command is running and waiting to finish its job before it gives me back my shell prompt. Now if I want to continue working, I can type the letters Ctrl-Z. Control Z stops the shell job and waits for me to do something upon it. What I can do now is I can run a BG for background. BG always runs on the last shell job. So at this point I can type jobs to get an overview of all shell jobs that are running, and I can see that my sleep 600 command is running in the background. You can run jobs immediately in the background as well. Let me do ddif equals dev0, which stands for input file dev0, of equals dev0, which is the output file dev0. And if I put an ampersand behind it, it runs as a background job. You can see that I now have two jobs running in my shell. If there's one of these jobs that I want to be running as a foreground job again, that's not too hard to do. I use the fg command. fg1, for instance, puts the sleep 600 command in the foreground again. So I can manage this job as well. If I don't want it to be running anymore, I just type Ctrl C and it is gone. And this is basically what you need to know about running shell jobs. On your server there are jobs and there are processes that run as background processes. To get an overview of all of those, you can use the ps command. If an ordinary user runs ps, he will see just his own processes. If the user root runs ps, he will be able to see all processes. PS has many options, and I like showing you PSAUX, which basically shows you most of the processes that are running on this system. Because it is going to give us much information, I'm piping it through head, which gives us the header line as well. So what we see here is first the name of the user that started the process. Next, every process has a unique process identification number, the PID, which you can see here. PID number 1 is systemd. This is the first process that was started by the kernel, and that takes care of starting all processes. Then we have the amount of CPU usage and the amount of memory usage of this process, and we have some information about memory usage. Linux processes use two kinds of memory. There is the virtual memory size, which you can see here as VSZ, and there is a resident memory size, which is RSS. Just consider virtual memory the amount of memory that has been reserved by this process, but hasn't been really allocated in RAM. The resident memory is memory that has been allocated in RAM. Then you can see the TTY, which is a terminal that the process is running on. For normal commands you will normally see a terminal. If it's a background process you will see a question mark. Then we have the current status of the process. Most of them are in the sleep status, which is indicated with an S. We have the start time, the total amount of time that the process has been running, and we have the associated command. Now if you're looking for a process, what typically is the most important part of information is the PID, because as I will explain later, you can use the PID to do process management. So you would do PSAUX grab something. Let's try HTTP, which shows us all HTTPD processes, which is the web server. So what we can see here is that most of the web server processes are running as user Apache, and this is the PID that is associated to the web server. You can see the CPU percentage and all the other information that we have just seen for the other processes as well. Let's have a look at the grep command, which has the status R, which means it is actually running. Well, it was running at the moment that the ps command provided this output. You can also see that it is associated to PTS/0, which is my current terminal, which by the way I can verify by using W. W shows me that there's a PTS0 device, which is a GNOME terminal. Session started as Lisa, but I have used SU- to become a root, and that is why we still see the user account of Lisa. So this is basically how you can see and get process information using PSAUX. On some occasions you will want to see relations to parent and child processes. Because if you terminate a parent process, typically all child processes will be terminated as well. You can use PSFAX for that information. So you can see here at the end of the list that there was a bin bash process that is started, and from there there's a minus that was started and another bash that was started and the command psfax that was running. Now in some cases, if a sub-process gets stuck, you just kill the parent process and the entire tree under the parent process will be terminated as well, which is a useful way of managing processes. There are many other switches that you can use with the ps command as well. I don't want to dive into them. Typically this is a command where you just make your choice of preferred switches and you stick to that, and if you're happy with that, you probably will be able to get all the information you need by just using those switches. So don't make things too complicated.
So let's try to get an overview of Linux memory usage. A good starting point to get an overview of what your system is doing is the command free-m. -m stands for megabytes. It will give the output in megabytes. The first line is showing us what exactly is happening in memory. So what we can see here is that there's a total of 1834 and in use is 1757. So whoa, we only have 76 megabytes of memory left. That's not much. But we can also see that there's some memory that is used as shared memory. That is basically libraries that is shared between different programs. We don't have any buffers right now. Buffers is typically what you get if large amounts of data still needs to be committed to disk. And we have a lot of cache memory. Now cache is something very interesting to understand about Linux. The idea is that files that have frequently been accessed on your Linux system, they are cached in memory. So basically if you want to access a file, the file has to be transferred from disk to RAM, and Linux keeps it in RAM as long as possible. And that's what we call cache. But what you see here is that we right now have 1 gigabyte of cache, and that is a lot. And it seems like we only have 76 megabytes of available RAM, and that's not much. But does that mean that at this point it wouldn't be possible to charge a program that needs 200 megabytes of RAM? No, it doesn't. Because cache is used for optimization of your system. So by allocating lots of cache, your system can work in the best possible way. But cache can also be freed at the moment that it is required for something else. And that is what is expressed in the next line, the minus plus buffers cache. It tells us, well, what is really used is 735 megabytes of RAM. But if we consider the amount of memory that is in cache as memory that can be used for something else, well, really, we have 1 gigabyte of RAM available. It's a bit of a rough indication because, believe me, you don't want to clear everything that is in cache. Cache is useful. Because if you have files that are frequently accessed, you don't want to go get them from disk all the times. Because disk memory is 1000 times slower approximately as memory that is in RAM. So using cache is good, but using much cache isn't always necessary, and the operating system can easily free the cache that isn't required for something else at that moment. Then we also have swap. Now swap is also something very useful. This is emulated RAM that sits on hard disk. So it is slow, but the Linux kernel is dealing with swap in a very smart way, and it will only put memory blocks that aren't actively being used in swap. And that means by moving unused memory pages from RAM to swap, that your RAM is made available to do other things that are useful, and that is good for the overall performance of your Linux system. So let's try to understand performance load on a Linux system. That is what is displayed if you use a command like uptime, as I will show you shortly. So when you are launching some task, it will enter the run queue. And if you launch another task, it will enter the run queue as well. And the result is that we have a run queue with different processes in there. So this graphic represents a run queue with PID 2, 3, 4, 2, 3, 5, and so on. And all are waiting for their turn. So the scheduler is what is taking care of running these processes. And the scheduler is the part of the kernel that will put the process on CPU 0 or CPU 1 or CPU 2 or CPU 3, depending on the amount of CPUs that is available in your system. Now, to get an overview of the current state of system activity, there is the uptime command. And in the uptime command, we see three parameters: 3.98, 2.66, 1.15, which is the average for the last 1, 5, and 15 minutes. But what exactly does it mean, the 3.98? Well, it's the amount of runnable processes in the run queue. A runnable process is a process that is either waiting to be served or that is being served on an actual CPU. So if you look at the average here, 3.98 for the last minute, that's a bit of a heavy load, but since we have 4 CPUs in total, it doesn't really matter in this image. So this is not a system that is suffering from bad performance. And if you look at the long term, over the last 5 minutes we had 2.66, over the last 15 minutes we had 1.15. This is not a system to worry about.
For a real-time overview of what is happening on your system, you can use top. Top shows you a list of top active processes on a system. By default it is sorted on CPU utilization, so you can see the busiest process mentioned on top of the list. In order to make it a little bit more clear what is happening, let me just start a few background processes. It's a copy from the dev0 device to the dev0 device, which, as we've seen before, is a job that will run without stopping. We can see them listed here as the top active processes. Now, from top there's a couple of parameters that you might be interested in. First, there's the load average. Load average shows you the average load for the last 1, 5 and 15 minutes. The interesting thing is, what exactly does it mean? I mean, 1.92 as the load average, what exactly is it? Well, it's the amount of processes that are on average in the run queue. The run queue is where all processes enter before they can be served by the kernel. And there's just one process from the run queue that can be handled at the same time for each CPU core. So in order to interpret this information, you need to know how many CPU cores you've got. Press 1 from top and you will see every single CPU that is available displayed on a single line. As you can see, in this case it is just CPU 0. So I'm looking here where we can see CPU 0. If I press 1 again, it gives me the summary of all CPUs. So what does it mean? Well, it means that a load average of 3 for one CPU is too much work for this CPU. And that is also why you can see that the 3 processes are dividing the available CPU cycles between them. There's some more information that you can get from top, like the uptime, which is just 15 minutes right now, and we have 2 users that are logged in, and we can see the total amount of tasks, and we can see the memory usage as well. Now, in order to say something that makes sense about memory usage, I would need to go very deep, but let me just give you a small impression of what we're talking about. So this is the total amount of memory, and of the total amount of memory we have almost half that is being used. That is 859 megabytes of used memory, and we have 1.2 gigabytes of memory that is still available. This is very typical because this system has been running for 16 minutes only. If you want to have a real impression, you should have a look at a system that has been up and running for a longer time. Now, of this used memory, some memory is in cache and some memory is in buffers. Cache and buffers is very important for a Linux system. And you should always have at least 30% of memory available for caching memory pages. The idea behind that is that at the moment a file is requested, the file has to be fetched from the hard disk. And the hard disk typically is a very slow medium in a computer, and that is why, for performance reasons, you want to avoid getting files from hard disks as much as you can. And that is why cache is used. Recently obtained files are stored in cache so that the next time a user requests access to the same file, it can be fetched from cache, and that is much faster. So cache is, as they call it, structured data. It is data like file names which the operating system can put a pointer to. Then we have buffers as well. Buffers is for unstructured data. It's like tables that I needed to get files from wherever they are, and it's also files that still need to be written to disk. Then we also have swap. Swap on a Linux system isn't bad. In fact, it can even be good, because the Linux kernel is very smart and it will only put memory pages in swap that really don't have to be there. Unless there's serious memory stress, of course, and then the Linux kernel needs to deal with it in another way. But typically you will only have inactive memory in swap. So it's good to have swap because it makes more memory available for useful things like caching memory pages. So in this case we don't use swap at all, but don't be afraid if on the server you see that some swap is used. There's nothing wrong with it. Another interesting line is the CPU's line, where you can see what the CPU is currently doing. We see the activity of the CPU divided over several aspects of the CPU. US stands for user space. This is typically programs that have been started by normal users. Nothing to be afraid of. Then we have SY, which stands for system space. This is programs that typically deal with hardware directly. Now, as I have used the DD commands to move over information from one device to another device, that is very direct involved to hardware, and that is why on this system I have a high activity on the hardware. Normally you shouldn't see that. The next one that is interesting is ID, which is the idle loop. That's the percentage of time that this system is doing nothing. An important one is WA, which stands for waiting. That's the amount of time that this system is waiting for I/O. That means waiting for a slow disk or a slow network or whatever. The other three items in this list are not that important. Let's talk about signals. Signals are instructions that can be sent to a process. They are mandatory instructions, so the process cannot choose to ignore them. There's a man page about signals, which is in section 7 of man. It gives us a list of all the signals that are available from the perspective of the Linux kernel. So there we go. Here you can see all the standard signals. Of all those signals, there are only a few that are common. The most common signal is SIG_term. That's the kind request to a process to cease its activity. If the process doesn't obey to that, you can use SIG_kill, which will just terminate the process. And there are some other signals as well, like SIG_hub, which tells a process to reload its configuration. But basically, as an administrator, you will use SIG_term and you will use SIG_kill. So how would you use them? Well, let's go back to top, where I still have my DD processes running. From top you can do some management of your system. For example, you can send signals from top by pressing K. K stands for kill. Kill is not the best name that you can imagine because you're just sending signals. But hey, it's the way it is, so press K if you want to send a signal to a process from top. Now let's have a look at process 2908 and assume that this is a process that we don't want to have anymore. You can enter the name of the process in here. You can even see that top has suggested it as the default PID. So let's do something else like 2909. And then it asks us what exactly we want to send to the signal. So by default it will send signal 15, which is SIG term, which is like, dear process, please stop. Press enter, and as I told you, it's mandatory, so the process just stops. Now let's do something else, and let's press K again, because I want to show what is happening if you're sending signal 9. I'm doing it on process 3152 this time, which is top itself. The basic idea behind signal 9 is that the process won't have any opportunity to save its work. It will just be kicked out in a rough way, which isn't good. So when I'm doing 9, you can see the result. You see that nothing was cleaned, and I just have my prompt in the middle of the previous output of the top command. Now this is just top, and for top it doesn't really matter, but imagine what it would mean to processes that are working on open files, for example. Those files risk getting destroyed, so you really shouldn't use the SIG kill signal too much. So you can send signals from top, you can also send them from the command line. If you want to do it from the command line, kill is your utility. Let's do kill -- help, which tells us it's an invalid signal specification. Did you see that? This is one of the few commands that doesn't have the -- help option. So let's do man kill, and you can see how we should use the kill command. So basically it needs a PID, which is a process ID. So you don't need the name of a process, you need the ID of a process. So if I want to kill a DD process, I first need to look up the PID of the process in question, which is, for example, 2907. So I can do kill 2907, and then it's gone. And if I want to send a -9, then I just have to add that as an option to the kill command. And you can see it is terminated, and when I go back to top we shouldn't have any DD commands anymore. Now let's do some of those kill commands again, because I want to show you something else. So I need command 995 from history. Oops, that was the wrong command. So let's try command 996 from history and run that a couple of times again to create some workload. You can see in top that the system is very busy right now. So what if I wanted to kill all of those at the same time? Well, that's very simple. You would just use kill all. Kill all DD will terminate all processes that have the name DD. So it does an exact match. It doesn't kill processes that have DD somewhere in the name. It only kills processes that have the name DD. And we can verify that from top. And that is how you send signals to processes.
Now let's explain understanding priorities and niceness. Imagine that you are in line at Starbucks waiting for your coffee. Another person comes in and he's standing behind you waiting for his coffee as well. Everyone is waiting for his turn. By default, everyone at Starbucks has the same priority. First come, first served. And now there comes this lady, and this lady is in a hurry. And she's skipping the line and yells at the desk, "Can I have a cappuccino to go, please?" Would you consider that a nice lady? Probably not. And this is exactly how it works with process priorities and niceness. By default, as you will see in my next explanation, every process has the same priority, but you can adjust the priority as a system administrator. You can give a negative niceness to a process to have it served first. And you can give a positive niceness to a process, which means that it lets other processes go before itself. And that is a very useful skill as an administrator, so that you can adjust the processes a little bit and make sure that important processes are served first before the other ones.
Let's talk about process priority. If you look at the top utility, you can see the PR column. In the PR column you can see the priority of all the processes that have been started. Normal processes by default are all started with the same priority, which is 20. And then there's also real-time processes, which you can recognize by RT in the PR column. So since normal processes, well, almost all normal processes, we do see an exception here, but since all processes are started with the same priority, they all get their fair share of CPU cycles, which we can see in the DD commands that are running here. All of them have about 1/3 of the available CPU cycles. In some cases it may be necessary to increase or decrease process priority. Imagine, for example, that you just started a query and users start calling that your server is so slow. Then you might decrease process priority for your query a little bit. Or imagine that you need to rush a job through, you might increase the priority a little bit. In order to do that, you can nice processes. And by nicing processes, you will adjust the current priority. You can use a negative nice value, which makes the process more aggressive, and you can use a positive nice value, which makes the process nicer. So let's see how that works from the top interface, because you can adjust nice values from top by pressing R. So it asks which process to change the nice value for. Let's do 3387. And then it asks which nice value we want to have. So nice values go from -20 to +19. Don't use -20 immediately if you want the highest possible priority. Just start by increments of 5. So I want to increase the priority of process 3387. So I type -5. And we can see that the priority has become 15, which means that it has a higher priority, and you can see it immediately gets more CPU cycles. So if this is what you want, then you're good. If this isn't good enough, you can do it again. At any time, the nice value that you are going to use is going to be relative to 20. So let's do it on 3387 again, and let's do -7 this time. You can see 20 minus 7 equals 13. So this gives a little bit of more CPU cycles again. So this is how you can do it from the top interface. You can also re-nice from the command line, or you can use nice when starting a command. So let's do nice --help, which tells us that we have nice followed by an option followed by a command, and the niceness is an adjustment that we specify using -n. So if I do nice -n10 dd if equals dev 0 of equals dev null and run that as a background job, it should be nice, and we can see that from top if all went well. So do you see that? We have process 3425 now with a priority of 30 and an adjacent nice value of 10. You can also see some of the activity of nice processes here in the %CPU activity column. The last thing you need to know about nice is that you can use it on running processes as well. In order to do that, you have the re-nice command. And re-nice --help shows us that we have a priority that you can specify, and you can run it directly on any PID. So re-nice -n -10 on 3425. And you can see that the old priority was 10, the new priority was minus 10, which isn't entirely correct, but it's not the old priority, it's the old nice value. And you can see that from top we should have this process running as the most active process with a priority of 10. Now there's one thing that you should realize: nicing processes is very nice, but if you have to do that all the times, you might want to reconsider the average workload on your server, because you might be better off moving some heavy use resources to other servers.
So let's have a look at the exercise. I would like you to first type the command ddif equals def0 of equals def0. Change it from a foreground job to a background job. And then do that 3 more times, but start them directly as a background job. Once you've done that, you can use jobs command to get information about current background jobs. And then you can start top to do some process management. So from top, perform the following task. First, you can adjust the niceness of one of the dd commands you have just started. Adjust it to -5 and observe what happens. And then you can send a sick kill signal to the top command and observe what happens as well. And from the command line, you can next terminate all of the remaining dd processes. And that gives you an impression of some of the management tasks that you can do related to processes on your system.
The first question in the exercise was to run the dd command that we have seen a couple of times already as a foreground job. There we go. And we need to change it to a background job. So in order to do that, Ctrl Z will temporarily stop it and BG will put it in the background. Next we need to run this command 3 more times directly as a background job. So we put an ampersand behind it to 3 more times. And we need the jobs command to get information about current background jobs, which should give a total of 4 background jobs. Next, from top we need to do a couple of tasks, which is adjust the niceness of one of the dd commands to -5 and observe what happens. So to adjust niceness from top, you would press R for renice. And we just pick any one of them. So let's do 3630. And it should have a nice value of -5. And what is happening? Well, the amount of CPU cycles for this process will increase. Next we need to send a sick kill signal to top. Let's do that from top by doing K and select the top process. Oh, we don't see the top process, so let's get back here and wait until we do see the top process. There it is, 3641. So we take 3641 and we want a sick kill. By default, sick term, the nice way of asking, is sent to the process, and we want a sick kill, which is number 9. And there we can see the result. Nothing is cleaned and it's a total mess until I do Ctrl L to clean my desktop. And now from the command line, terminate all remaining dd processes. That would be kill all dd. I get back in top and we can see there's no more dd processes left. And you will also see that the load average is slowly going to decrease. That will be slow because it's an average for the last 1, 5 and 15 minutes.